Hello, Ellie here. Today we're going to talk about aqueous solutions. When balancing a chemical reaction, we've seen states of matter like solids, liquids, and gases, which are abbreviated as S, L, and G respectively, accompanying the reactants and products. But there's also a fourth one, which is AQ. What does this mean? What are other ways we can write a chemical reaction? This is what we'll explore today. First, some terms to know. An aqueous solution is a solution that's dissolved in water. This is abbreviated as AQ, as mentioned before. States of matter are solid, liquid, and gas, and aqueous is technically a state of matter in chemical reactions only, although it's not a state of matter in terms of the actual states of matter. And these are abbreviated as S, L, G, and AQ, respectively, as I also mentioned before. An ionic bond is a bond typically between a metal and a nonmetal, and it's usually made of two parts, a cation, which comes from the metal, and an anion that comes from the nonmetal. A polyatomic ion is a covalently bonded molecule, which has a net charge that isn't neutral, making it an ion. This is treated as one unit, and it cannot be separated into single elements. The oxidation number is the charge of an ion. And the precipitate is a solid which forms from a chemical reaction. So this would not be soluble in a solvent, like water, for example. And finally, a spectator ion is an ion that's present on both sides in the same form, which means it doesn't actively participate in the reaction. So let's discuss what exactly is an aqueous solution. Well, as mentioned before, an aqueous solution is a compound dissolved in water. Now, this is soluble. If it was insoluble, it would not be an aqueous solution. It would be either a precipitate or just insoluble in water. Another part of an aqueous solution is that a compound, if it's ionic, is separated by the polar water molecules. So the water molecules technically hold the cation and anion in place, and the partially positive hydrogen attaches to the anions, which is the negative side, while the partially negative oxygen attaches to the cations, which is the positive ion. And this bonding keeps the ions separate from each other so that the compound can dissolve. Over here is a diagram of a general ionic compound being broken up into its cation and anion by the water molecules. As you can see, the anion is negative, so the partially positive hydrogen attaches to it, while the cation is positive, so the partially negative oxygen bonds to that. Now, there are three different ways we can write a chemical reaction for the purpose of this video. The first way is a chemical or molecular equation. This requires balancing, and all reactants and products are written as compounds. So, for example, potassium sulfate in aqueous form plus barium chloride in aqueous form goes to barium sulfate in solid form plus 2 potassium chlorides in aqueous form. The next step is a complete ionic equation. This is one step further than a chemical equation. So all aqueous compounds are divided into cations and anions. And one thing to be careful about is not forgetting the charges or oxidation numbers. So if we were to write the complete ionic equation of the above chemical equation, we would get 2 potassium ions in aqueous form plus 1 sulfate ion in aqueous form plus 1 barium ion in aqueous form plus 2 chloride ions in aqueous form, which go to barium sulfate in solid form plus 2 potassium ions in aqueous form plus 2 chloride ions in aqueous form. As you can see, the barium sulfate, the solid, is kept together. It's not broken up into ions because the water won't break it up. It's a precipitate and is therefore insoluble in water. The last one is the net ionic equation, where all spectator ions are removed. So what that essentially means is that the ions that appear on both sides of the equation, like this 2K plus on both sides and 2Cl minus on both sides, we can cancel those out and we'll just be left with the barium ion plus the sulfate ion going to barium sulfate, which is in solid form. Alright, let's try some practice. First, let's write the balanced chemical equation, complete ionic equation, and net ionic equation of this following reaction. Sodium carbonate in aqueous form plus barium nitrate in aqueous form going to sodium nitrate in aqueous form plus barium carbonate in solid form. So the way we balance chemical equations is by manipulating the coefficients of each compound in such a way that each element will have the same amount of atoms on either side. This fulfills the conservation of mass principle, which essentially states that mass cannot be created or destroyed. So the mass of everything on one side has to be equal to the mass on everything on the other side. So let's start with counting how many of each atom there are, disregarding any polyatomics or bonding. So first, we can count the sodium. So since there's a subscript over here, there are 2 sodium atoms. So let's write that down. We have 2 sodium atoms. Over here we have 1 carbon atom. So again, we're disregarding the polyatomic. Carbonate is a polyatomic, but we're going to ignore that for now. And we have 1 carbon atom on this side. We have 3 oxygen atoms. We have 1 barium atom. And now we have to be careful over here because the subscript applies to all the atoms in this parentheses. So the nitrogen, there isn't just one of it, there's 2 of it. And the oxygen, there's 3 oxygens in one of this, but since there's 2, we're going to multiply these subscripts together to get 6 oxygen atoms. Alright, so now that's everything on this side. Now let's find how much of everything is on this side. So for sodium again, we have 1. For nitrogen, we have 1. For oxygen, we have 3. For barium, we have 1. For carbon, we have 1. And oxygen again, we have 3. Now we can combine these together, but usually it's best to keep them separate, since you can keep track of them easier. Given the amount of atoms on either side, I challenge you to balance this equation before I go through it. Alright, let's go over this. So on this side we have 2 sodium atoms, but on this side we have 1. Now an easy fix is to multiply whichever compound has sodium in it by 2, so that we'll have 2 of these. So let's do that first. We have 2 sodium sulfates. Now what this does is it changes this sodium atom to 2, and we have 2 nitrogen atoms as well. And then we also get 6 oxygen atoms because there's 3 here before, and then we multiply that by the coefficient 2. So we have 6 over here. Now let's see if there's anything else we need to fix. So we have 2 sodium atoms over here. We have 1 carbon atom over here. We have 3 over here and 3 over here. We have 1 barium, 2 nitrogens, and 2 nitrogens, and we have 6 oxygens and 6 oxygens. which is perfect. So that 2 is all we needed, and the rest of these are 1s. Alright, now that we have this balanced chemical equation, let's write the complete ionic equation of it. So we're going to take all the aqueous compounds in this equation and we're going to break them up into their respective cations and anions. So let's look at this ionic compound first. Now, the cation is the metal and the anion is usually the non-metal, unless there's a polyatomic ion, in which case it's a covalently bonded compound. So for sodium carbonate, carbonate is our anion, and we can essentially break it into 2 like this, and we count how much of each cation or anion we have. So for this one, we have 2 sodium cations. So we're going to write this as 2 sodium, and the oxidation number or charge of sodium is 1+, so we're going to put a plus over here. Now for carbonate, we have 1 carbonate ion, or 1 carbonate anion. So we're going to put 1 carbonate anion, and the charge of carbonate is 2-. Yep, and I forgot to put the states of matter over here. So both of these are aqueous, and because they're aqueous, we're breaking them up into their respective ions. Now let's look at this one. So this is also aqueous, so we can break it up, and we have 1 barium cation due to this coefficient, and we're going to write 1 barium cation, and the charge of barium is 2+. And this is also aqueous. Then next we're going to look at the nitrate, and we have 2 nitrates over here, which is why it's in this parentheses. So we're going to write 2 nitrate anions, and the charge of nitrate is a -1. And this will go to, we're going to look at this side now, and over here we have a coefficient, so we're going to have to multiply each cation and anion by 2. So the sodium cation, there's 1 of it, but since there's 2 of this compound, we're going to write 2 sodium cations. And again, that has a +1 charge. Oop, forgot it over here. Okay. And then we're going to look at the nitrate. We have 1 nitrate over here, but since there's 2, we're going to put 2. And again, this is a -1 charge. And then we have the last one, and this is a solid, so we can't break it up into its respective ions. So we're going to keep this together as BaCO3. And this is solid. Now, typically, you don't have to write the state of matter for all the aqueous ones since it gets a bit tedious, but you should definitely include the state of matter for the one you're keeping together. Alright, now that we have a balanced chemical equation and a complete ionic equation, let's write the net ionic equation, which means we have to find the spectator ions, cancel them out, and then write the net ionic equation. So let's see which ions are on both sides of the equation. So we have 2 sodium plus in aqueous form, and let's look at this side. We have 2 Na plus in aqueous form on this side too. So this goes unchanged throughout the reaction, and we can cancel them out. And this carbonate anion in aqueous form is not an ion on this side. It's in the compound, so we have to keep that. And the barium ion is also in the compound, so we also have to keep that. For the nitrate ion, we have 2 of these in aqueous form, and we have 2 of these in aqueous form as well, so we can cancel these out. That leaves us with a net ionic equation of barium to plus in aqueous form plus carbonate ion to minus in aqueous form going to barium carbonate in solid form. All right, let's move on to the next one. We're going to do the same thing we did in the previous one. We're going to write the balanced molecular equation, complete ionic equation, and the net ionic equation of this reaction. Hydrochloric acid is added to aqueous calcium hydroxide, forming water and aqueous calcium chloride. Now, before we go through this, I encourage you to pause the video and try this out by yourself. All right, let's do this. Now, we have an extra step to do. We have to write the equation ourselves because it's given to us in word format. So we can use the nomenclature to figure out what compounds are reacting to make what products. So let's look at this first one, hydrochloric acid. Now that means it's an acid, so it's going to have hydrogen, and this chloric means chlorine, so it's going to have chlorine as well. Now the hydro prefix means that we're going to have it without oxygen, so it's going to be just HCl. And HCl is one of the more popular acids, so you've probably heard of this formula. And this is aqueous because acids are always aqueous. Now this is added to aqueous calcium hydroxide, and since the state is given here, we will write that as aqueous. Now calcium is simple enough, we're going to have calcium in there, and hydroxide is a polyatomic ion with a charge of -1. Now calcium, if you recall, has a charge of +2, and we need our compounds to be net neutral, which means they have an overall charge of 0. So to balance this out, we need 2 hydroxide anions to combat the +2 charge of this calcium cation. So we're going to put that in parentheses, and we're going to put OH over here, and we're going to put 2 of those. And this is aqueous, and this will go to water. Now, when you have just water here, it's not aqueous, because aqueous means it's dissolved in water, and you don't dissolve water in water. So we're going to write water as liquid, and we all know what water is. We know that's H2O. That's liquid. And then lastly, we have aqueous calcium chloride. So this is calcium, of course, and then chloride is chlorine. And again, if you recall, chloride anion has a -1 charge, while calcium cation has a 2+ charge. So we're going to put 2 chloride anions to combat the 2+ charge of the calcium. And this is going to be aqueous as well. Now let's go on to balancing this equation, since we have everything written. So what we're going to do is, like in the previous one, we're going to figure out how much of each atom is on each side, and then we're going to work to balance that out. So let's look at this side first. So we have a hydrogen over here, and we have a hydrogen in here. So we're going to disregard polyatomics. So there's a hydrogen here, and there's 2 hydrogens over here. That means a total of 3 hydrogens. And for Cl, we have 1 Cl over here. Then we have calcium, we have 1 of that. And we have an O over here, and we have 2 of them since it's in the parentheses. And since we already counted the hydrogen in here, over here, we're going to leave that be. All right, now let's look at this side. We have 2 hydrogens over here. We have 1 oxygen. We have 1 calcium, and we have 2 chloride anions. Okay, now let's see what is unbalanced and what is balanced. So we can see that the hydrogen, oxygen, and chloride anions are unbalanced. So what we can do first is we can start with the chloride, because that usually is the easiest. You don't want to touch the oxygens until the last, because that's usually the hardest to balance. So we're going to start with the chloride over here. And in order to balance these across the sides, we can multiply the compound this is in by 2. So we're going to put a 2 over here. And over here, that's one of the hydrogens that's being multiplied by 2. So this is going to become not 3, but 4, since we're adding 1. And this chloride anions are going to be 2 over here, so this is balanced. Now, the hydrogens and oxygens still are not balanced. And we can see that there's a factor of 2 going on between here. So hydrogen has 2, hydrogen is 4, oxygen is 2 over here, and oxygen is 1 over here. So on this side, we can multiply whichever compound has the hydrogen and oxygen by 2. And that happens to be the water, which is all in one compound, which is great for us. So if we multiply this by 2, we get 2 hydrogen and 2 oxygen. Now all of them are balanced, and we have our balanced equation here. So that's 1 and 1. Now, one important thing before we move on to the complete and net ionic equations is that H2O can also be written as HOH. So if you wanted to keep the hydroxide together, you'd have to know that the water is composed of 1 hydrogen and 1 hydroxide. So that way you can balance the hydrogen with each other and you can balance the hydroxide. Now let's move on to the complete ionic equation now that we know this. So we are going to look at all the aqueous compounds and we're going to break them up into their respective cations and anions. So for this one, we have 2 of these, so we're going to take that coefficient into mind, and we have 2 hydrogen cations over here, and that has a +1 charge. So there's 2 of them, and we're going to put 2H+, and this is aqueous. And then we're going to add, this 2 still applies, and we're going to have 2 chloride anions with a -1 charge. And then we're going to go on to this one, and the calcium cation has a 2+ charge, and there's 1 of that. So we're going to put calcium 2+, and that's also aqueous. And then the hydroxide, there's 2 of them, and we're going to keep this together because it's a polyatomic ion with a -1 charge. So we have 2 hydroxide ions, which is also aqueous. And this goes to 2 water. Now, since this is liquid, we can't break it up. So we're going to keep that as 2 water molecules. And this is liquid. We have our aqueous one over here. And so we have our calcium cation, which is a 2+ charge, and that's 1 of that. So that's calcium 2+, and that's aqueous. And then lastly, we're going to look at our chloride, which is 2 of them, and so we're going to have 2 chloride anions with a -1 charge, and that's aqueous as well. All right, now let's figure out what our spectator ions are. So we have 2H+. Now, where's 2H+? Can we find 2H+ on this side? No, we can't. That's in the H2O over here. So we're going to keep that. As for the 2 chloride anions, we can easily find that over here. So we're going to cancel those out. And the calcium ions, there's 1 over here and there's 1 over here. So we're going to cancel that out too. And the 2OH-, that is in the compound over here. So we have to keep that. So if we put that all together, we get 2H+ aqueous plus 2OH minus aqueous goes to 2H2O liquid. Now this is technically correct, but what would be even more correct is if we got rid of these coefficients, which are all 2, and we simplified it to become H plus aqueous plus OH minus aqueous going to H2O in liquid state. Alright, that's all I have. Thank you for watching. If you liked this video or this helped you, please click the like button. If this didn't help you, click the dislike button. I appreciate the feedback. And if you want more updates on new videos, please click the subscribe button. If you have any suggestions on what videos I should make, please put those in the comments or tell me somehow. And that's all I have. So until next time, see you.